Hello everyone, I am Yuvraj working as assistant professor in School of Physical Sciences, Punyaslok Ahilyadevi Holkar, Solapur University, Solapur. Okay, in today's presentation, we discuss about the one of the powerful characterization technique, and that technique is the atomic force microscopy, and simply we can say that the AFM techniques. Okay, in general, there are various type of the characterization tools in the material science, and that characterization tools are X-ray diffraction technique, scanning electron microscopy, transmission electron microscopy, EDS technique is there, X-ray photoelectron spectroscopy is there. By using that different type of the characterization tools, we get the different type of the information of the material. For example, by using XRD, we get the crystal structural information of the material, like defects, crystallite size of the sample material we can get by using the X-ray diffraction technique. Okay, by using the scanning electron microscopy, we can get the morphological analysis of the sample material. Okay, by using transmission electron microscopy, also we get the morphological study of the sample material. Okay, by using the EDS, that is energy dispersive spectroscopy, we get the information about the element that present inside the material. By using the XPS, we get the chemical composition as well as chemical state of the material. Okay, like that, atomic force microscopy is one of the powerful technique, and by using that AFM technique, we get the three-dimensional topography of the sample material. The atomic force microscopy, the name includes the two dominant words. One is force and other is atomic, means there is a force. Okay, and that force measures in the range of atomic level. Okay, and that atomic force microscopy is one type of the scanning probe microscopy technique. And in general, all the techniques in the SPM based on the scanning the probe just above the surface, while by maintaining the interaction between the probe and the sample material. Okay, and this presentation of atomic force microscopy contains the principle of the AFM, construction and working of AFM, different type of mode of the operation of AFM, and finally we discuss on the advantages and some disadvantages related to that atomic force microscopy technique. Okay, and that atomic force microscopy was invented by scientists beginning in 1986. Okay, and that AFM, recently the AFM is used to map and study the three-dimensional surface topography at micro or nanoscale meter for various types of the materials, and that various type includes the metals, semiconductor, conductive and non-conductive materials in a different environment like air, liquid and vacuum. Okay, let's discuss about the principle of that atomic force microscopy technique. Okay, that AFM uses a cantilever with a very sharp tip, and that tip is used to scan over a sample surface. As the tip approaches the surface, the close range attractive forces between the surface of the sample and tip causes the cantilever to deflect toward the surface. However, as the cantilever tip is brought even closer to the surface, okay, in such a way that the tip is in contact with the surface, then increasingly repulsive force take over and causes the cantilever to deflect away from the surface of the material. Or simply we can say that the AFM technique measures the atomic forces between the cantilever tip and the sample by using a laser to detect the lever motion, and the image formed in that atomic force microscopy is by scanning and using a feedback loop system, okay, to maintain a constant tip sample forces during the contact mode operation, or by maintaining the constant tip oscillation in case of a tapping mode during the scanning process. Let us discuss about the construction and working of the AFM. Okay, the schematic representation of the atomic force microscopy is shown in screen. Okay, that consists of a cantilever, tip, laser, photodiode, and there is a detector and feedback system. Okay, that AFM consists of a cantilever with a very sharp tip at one end, and that tip is used to scan the surface of the material, and the cantilever is typically silicon or silicon nitrate with tip radius of curvature on order of the nanometer, that is in the range of 20 to 60 nanometer. And the typical length of the cantilever is generally 100 micrometer to 200 micrometer, and the cantilever tip is very thin and short. Okay, the tip is thin so that a small constant force is provided such that a large deflection are obtained with the small forces, and the tip is short so that there is a high resonant frequency in order to reduce noise vibration. Okay, and that cantilever tip is the pyramidal in shape with a tip half angle of 35 degree. Okay, and when the cantilever tip is brought into the proximity of the sample surface, okay, then the forces between the tip and the sample leads to the deflection of the cantilever according to the Hooke's law, means F is equal to minus kx. Okay, and that k is the spring constant of the cantilever, and x is the deflection, cantilever deflection. Okay, and in that atomic force microscopy technique, the various types of the forces are measured, and these forces are the mechanical contact force, van der Waals forces, capillary forces, electrostatic forces, and magnetic forces also. And in the working, the cantilever scan across the surface by using the XY piezoelectric tube, and there is a laser and a photodiode system that are used to monitor the tip force on the sample, and bending motion of the lever or charging force detected by the laser beam reflected from the back side of the lever into the photo detector, and there is a feedback loop system between the photodiode and the piezo crystal that maintain a constant force during the contact mode operation of the AFM imaging, and by maintaining the constant amplitude during the tapping mode imaging process. And the topography images formed in the AFM techniques by displaying Z piezo voltage versus position. Okay, next is the AFM cantilever deflection measurement. The cantilever deflection measurement having one method, and that is the beam deflection method, or it is a very common method of the cantilever deflection measurement. And in this method, the laser light from a solid state diode is reflected off of the back of the cantilever, and that deflected light is collected by the position sensitive detector, that is PSD, and that PSD consists of two closely spaced photodiodes, and the output of that photodiode signal is collected by the differential amplifier, and the angular displacement of the cantilever results into one photodiode collecting is more light as compared to the other photodiode, and that produces a output signal, and that output signal is proportional to the deflection of the cantilever, and also the sensitivity of that beam deflection detection method is very high. Next is the modes of operation in atomic force microscopy. Okay, in atomic force microscopy there are three modes of operation, and that are the contact mode AFM, non-contact mode AFM, and tapping mode AFM, or tapping mode we can say that the semi-contact mode AFM. Let us discuss one by one. First we discuss about the contact mode AFM. Okay, that in that contact mode name includes that the tip makes the soft physical signal with the surface of the sample, and the deflection of the cantilever is proportional to the force acting on the tip via the Hooke's law, that is F is equal to minus kx. Okay, and earlier we discussed what is k. K is the spring constant of the cantilever, and x is nothing but the deflection of the cantilever. Okay, and in that contact mode AFM, tip either scan at a constant small height above the surface or under the condition of a constant force. Okay, in the contact mode AFM, The silicon nitrate tips are used for the scanning the surface of the material, and by using that contact mode AFM, atomic resolution image are obtained. This is one of the best advantage of that contact mode AFM, and the lateral forces can distort the image. Okay, this is one of the disadvantage related to that contact mode AFM technique. Next mode is the non-contact mode. Okay, in that non-contact mode AFM, the cantilever tip of the cantilever does not contact the surface of the sample, and the cantilever is isolated at either its resonant frequency or just above, where the amplitude of oscillation is typically a few nanometer, that is below 10 nanometer, and the van der Waals forces that are strongest from 1 nanometer to 10 nanometer above the surface, or any other long range forces that extend above the surface acts to the decrease the resonance frequency of the cantilever, and this decrease in resonance frequency combined with the feedback loop system that maintains a constant oscillation amplitude of frequency by adjusting the average tip to sample distance, and there is a low force is exerted on the sample surface, so there is no damage happen in the sample. Okay, this is the best advantage of that non-contact mode AFM, and also the non-contact mode AFM having the lower lateral resolution. Okay, that is limited by the tip sample separation. This is the disadvantage belongs to the non-contact mode AFM technique. And the third mode of operation is the tapping mode or semi-contact mode. Okay, in that tapping mode AFM, the cantilever is driven to oscillate up and down at or near its resonant frequency by the small piezoelectric field element mounted in the AFM tip holder. Okay, similar to the non-contact mode. However, the amplitude of this oscillation is greater than 10 nanometer, and it is typically in the range of 100 to 200 nanometer, and there is a electronic servo uses the piezoelectric actuator to control the height of a cantilever above the surface of the material, and this servo electronic servo adjusts the height to maintain a set cantilever oscillation amplitude as the cantilever is scanned over the surface of the material. In that tapping mode AFM, there is a high lateral resolution. Okay, and the range of that high lateral resolution is 1 nanometer to 5 nanometer, and this is best advantage belongs to the tapping mode AFM, and there is also one disadvantages, and that is the slower scan speed as compared to the contact mode AFM. Let us discuss about the some advantages of the atomic force microscopy techniques. The atomic force microscopy provides the three-dimensional surface profile of the sample material, and the sample viewed by the or in the atomic force microscopy technique do not require any special treatment like metal or carbon coating. Okay, and that would irreversibly change or damage the sample, and they does not typically suffer from the charging artifacts in the final image. This is one of the best advantage of that atomic force microscopy technique. That atomic microscopy technique provides the higher resolution. Okay, as compared to the same, and another advantage related to the atomic force microscopy is the they can also combine with a different type of the optical microscopy and spectroscopy technique, such as a fluorescent microscopy of IR spectroscopy, and that gives the or that giving rise to scanning near field optical microscopy, nano FTIR, and further expanding its applicability. And along with advantages, there are few disadvantages of the atomic force microscopy, and these are the first disadvantage is the AFM is the single scan image size. Second one is the scanning speed of the AFM is also a limitation, or that AFM requires a few minutes for a typical scan. Okay, and this is a very low speed as compared to the scanning electron microscopy, and the getting data is non-dependent of the cantilever tip. Okay, means the getting data is depends on the type of the tip material or type of the tip, and the during the scanning process tip of the cantilever can be damaged, and these are some examples of the AFM images. Okay, there are 2D and 3D AFM images of the copper oxide. Okay, this copper oxide material is synthesized in our FMRL material laboratories, functional material research laboratories, by using thermal evaporation technique. And this figure A shows the 2D image of the copper oxide, and figure B shows the 3D image of the copper oxide material. Okay, similarly there is a 3D images of the polyaniline material and nickel oxide materials, and these polyaniline and nickel oxide materials are also prepared in our functional material research laboratory in the our School of Physical Sciences. Okay, this is about the atomic force microscopy. Thank you.